So as I mentioned before, let's do a RC car for this semester's project. So what I will do is I will purchase um, some RC cars from Amazon, and you could disassemble the cars and reutilize those components, especially those remote control components and some of the motors in from the toy, and as well as some other parts if you want. But all the rest you need to design and fabricate yourself. Basically, you want to design the appearance, some of the critical parts like those transmission mechanisms, and also other parts like wheels. You can reuse the previous, I mean the existing wheel, or you print your own ones. And but what you want to do is utilize all the available 3D printer in the lab, the Prusa and the Formlab and the Markforged one, right? So these are the available ones you should be able to use for this project, and it is a group project. So you need to first form groups, and I need to know it in the next probably next week. You just tell the TA what are the groups. I mean, in the previous semesters, basically people just form groups based on their lab sessions, right? That's one possibility. Or you can form groups, whatever you want. 3 to 4 students per group, something like this. That's a fair enough amount of person per group. And basically everyone has to take charge of one or several tasks for the project. Basically, you need to write a statement about the team members' contribution, and that's important. And there are some situation in the previous lectures, previous courses, and there were team members who didn't contribute anything. Turns out the other member of that team tell me the situation, and I talked to the team, the one who didn't contribute, and it turns out that student didn't change, and there will be a deduction of points. That's not allowed. Basically, you have to do the teamwork and complete what you promised to do for this team project. And basically, besides the document, the files you submitted to the my courses, you also want to do a presentation, a virtual presentation together with a video to show how you design, fabricate, and use the car. Of course, there will be a session basically that is to try out the car you fabricated and see how long it can, how long the distance the car can run, how fast, how smooth, and the stability, so on and so forth. These are the criteria for this project. I think I used to give this task to the students 2 semesters ago. No, I think 3 semesters ago. But the thing is, at that time, that's the COVID, right? And turns out they have no chance to really fabricate it. but this time we have the lab session, we have the lab available. So I hope you could complete the design as well as the fabrication. Basically what I will give you probably will be a car like this, if you can see my screen. Basically, each of the group will have one car like this, and you could reutilize all the components in this car. If you need some other parts, please let me know, and I will let the department secretary to make a purchase. All right. Any question?
It's mandatory to use just Fusion, or we can use another like SolidWorks or
The
maybe
Fusion.
Fusion.
I
Okay.
mean, although there's no, I won't say there's a restriction, but the
Mhm.
Fusion would be I would say we have, every student has a license, right, for Fusion. So that will
Okay.
be the most convenient way. But if you do not want to use Fusion, you can discuss with your team members. And of course, you want to make sure you guys are okay with certain software. I mean, as long as it does the job. All right.
Okay.
Anything else? Any other question? No? Okay, I will post this to my courses. You can check it carefully. And there will be a Q&A session, I mean, office hour on Friday. Basically, that will be, let me check my office hour time. If I think it's 1 to 2, right? Yeah, I think that's 1 to, yeah, 1 to 2 Friday. So if you have any question regarding the project as well as the homeworks. Oh, by the way, I haven't posted the homework one, the marked homework one, and also the solution. I will promise you that will be done by today. And after, basically you will submit the homework 2 by tomorrow, right? And I will post the solution Wednesday, and such that you have all the solutions in hand for the exam 1. So that will be the similar questions in the exam 1 to what you have done in homework 1 and homework 2. All right. So if you have no problems with homework 1 and homework 2 and all the questions and the knowledges on the slides, you shouldn't be there shouldn't be an issue for your for your first exam. So again, the exam 1 will cover the let me double check the exam. So for the exam, basically you want to look at you want to check all the content and within the computational 3D computational aspects of 3D printing, which we just introduced last class. So everything before and within the computational aspects of 3D printing will be the one tested in exam 1. All right. Any question regarding this?
Yes.
Yeah.
I reviewed the different videos and I have questions about different things. So I can go to the to Friday to 1 to 2, you
Yeah.
say?
Yeah, 1 to 2. That will
Okay.
be the office hour, and you can just log in to this meeting room. I will be here, right here for you.
Okay.
Yeah.
Professor, I have a quick question.
Sure. Yeah.
For this class, when will the exam be?
Oh, that is next Monday, 1 week later.
All right, thank you.
Yep. So again, the questions, exam question will be posted on my courses, and you will given like 2 hours or something, same time as the lecture, and you complete it within that time and submit your solutions to my courses, just like the homework, same thing, but there's a time limit. All right, that's the formation for this exam.
And will you expect us to do it in Word like we were doing last time with equation maker?
You can use handwriting, no problem. But the only thing is you want to take a very clear picture or scan it. As long as I can see it clearly, what you write down, that's fine to use a handwriting.
Thank you.
Anything else? Okay, let's continue. So let's talk about the photopolymerization process, which is the one you will probably take a look at in the lab session. So the photopolymerization is also a very important additive manufacturing process. Basically, that is basically it looks like you have some liquid polymers in a resin, and certain light source will be utilized to cure the liquid resin, and turns out the liquid material will be solidified to the solid. That's the typical process for this 3D printing. And there are different ways to project the light source. There's vector scan or projected images. So for the vector scan, basically the laser is reflected to scan a pattern on each of the layer, and through the laser scanning, the material is cured, right? Or that could be an entire image, black-white image, projected to cure the layer. The black region means no curing, and the white region means the material need to be cured. So let's look at both of the two types of a process. So the very first stereolithography process is invented by 3D print. By the founder of 3D Systems. So an ultraviolet curable liquid polymer is selectively scanned from above with a laser beam with certain wavelengths to cure the material. And let's look at how it works. So as you can see here, the laser beam is scanning on this, on the surface of the resin, and the material is cured. And then this platform will, of course, there will be another step to lower the building platform, and then another layer of new liquid resin is spread on the top. As you can see here, that is the spreading of the material. So after all the layers have been cured, you will have the whole part. Of course, there could be some support material. I will introduce why we still need support for this process, but that's pretty much what you will have for the stereolithography. And there's some new development which has not just one laser spot, but dual laser spot. One is much bigger and the other one is smaller. So why we have such a different laser spot size? That is because for one layer, actually we don't care about the interior, I mean, the accuracy of the interior regions, right? We just want to have the interior region to be solidified, I mean, to be scanned such that the material will be solidified. The only thing we care about accuracy will be the one near the boundary, near the contour. So that's why we have two different lasers with different spot size. For the interior, we use a border spot to scan for the higher speed. And for the boundary, for the contour, we use a much smaller spot to cure the fine features. So that's why we have a multi spot size. And as you might also notice that the parts are dripping with those uncured resin at the end. So what you want to do? So you want to remove these uncured resin by wash it using the isopropyl alcohols, which we will also use in our lab session. And one thing you want to keep in mind is wear gloves, right? When you touch the part and wash the part using the isopropyl alcohols, because that could harm your body. So be aware of this when you operate the Formlab machines and touch the parts. And the post-processing for stereolithography. First of all, you want to remove those part material, and then probably for a better stiffness, you want to do a post-curing, right? Oh, of course, before that, you want to remove those uncured resin, and then you want to further harden the parts using a post-curing. It could be a ultraviolet or thermal post-curing. No matter how you want to further cure the parts such that its stiffness is become better. I mean, similar to other 3D printed part, you can sand it and use other process to further manufacture or fine tune it. Priming, painting, and plating. That's normal, right? For other 3D printed part, you can also do that with it. But that's pretty much the post-processing. Any questions?
Yes, I have two questions.
Yeah.
When I used in the past the basic resin printers,
Yeah.
and when some parts suggest to cleaning it with water, but why do certain parts turn white when mixing with alcohol and water? That's one of my questions. And the second is, it has happened to me that when these parts are subject to ultraviolet light, lose accuracy. I don't know if it's for the ultraviolet light or if it's for another thing, because I use this printer model for dental application, so it's very easy to match with the tooth the accuracy. So yes, you understand me.
Yeah.
Is for the ultraviolet light or what?
Yeah, I think that's a good question. Basically, you are pointing out some problems for the process. I think I got your what you were asking for the second question. That is when you use the ultraviolet violet lights, some of the parts are not as accurate as it's supposed to be, right? I think that is possibly because the shrinkage happens during the curing, and basically you want to do some of course, you want to make sure how you lose the accuracy, and to determine if the part has a shrinkage or not. If that's the case, when you do the design, you want to do some scaling up such that it compensates the shrinkage, just like what you did for those injection molding. I mean, basically in the injection molding, there will be shrinkage, right? But for this process, there is shrinkage as well. I mean, although it's not a thermal-based process. That's pretty much what I thought about for your second question. But for the first one, I don't quite get it. Can you ask it again?
Yes, in some cases I mix water with alcohol to wash the model. So in some cases the model was white. I don't know why. For example, if it's a clear resin, the new color is white. So yes, I don't know why.
Oh, that's interesting. I never meet such problem. So yeah, I mean, that might, I mean, I'm not 100% sure about it, but it might because of the material you used. There's some reaction between the alcohol and the material. I mean, it all depends on, I mean, that's I would say the most possible explanation of what you encountered. But in most cases in our lab, that shouldn't be such a problem. Or the alcohol you used has something there, not just a pure alcohol. That could be another reason. Or the water, you said you mix water into the alcohol. That, for example, you know, those water from the tap, that could be some, I mean, people need to clean them, right? So they put something there, and that could have some reaction with the material. So yeah, that basically you want to
I don't know. It's a basic resin. Is there any cubic resin, in fact? So I don't know why.
Yeah, that's
weird.
Yeah, something it happens. Yeah. Okay, but these are very interesting questions. Let's move on. So as you can see here, as you for the 3D systems process, the model is built from top towards down. Also, there are some parts built upside down in other process, also stereolithography. We call such a process the inverted stereolithography, and the Formlab is one of the, I mean, Formlab utilize such a process. So the difference is basically instead of basically the vat is lower into the resin, and there will be a I mean, lower into the resin tray, and there is a thin gap between the platform and the bottom of the vat. So then the laser will go through the clean bottom of the vat and scan and cure the resin. And then the platform will raise up to allow more resin flow in, such that there will be another liquid resin in between of the cured layer and the bottom of the tank. Then those liquid resin will be cured again, and after that the platform will move up again, and another new liquid resin will flow in again. So that's how it works. So maybe we look at this video.
This is the brand new Formlabs Form 2, and we're going to talk to some folks who built this amazing machine. I saw this thing when it was a baby, and now you have the Formlabs 2. What's going on over here?
This is really our third generation 3D printer. We had the Form 1, Form 1 Plus, and now the Form 2. The build platform starts lowered down all the way into the tank, and there's a layer of this liquid resin in the tank. And laser comes in from the bottom, and it scans across the bottom surface of the resin, and wherever it goes, it solidifies a layer of the resin, and it sticks to the build platform. And then you lift the build platform up one layer, and you repeat that process layer by layer.
There's kind of two big differences when you look at the machine. It's the experience of using it, but more importantly, what you get out of it. And so, if you want, I can crack open the hood. We redesigned the optical engine. The laser's 50% more powerful. Now we had to make our own custom galvanometers, and galvanometers are the mirrors that move the laser. A lot of 3D printers that use resin, they'll have a projector. Now the problem is with the projector is you can only get really small parts.
And like, we're literally talking like a DLP projector.
Right, exactly. And what you're seeing right now is it's drawing the laser. The next thing you'll see is the tank will slide. That's because it's separating the part. And when you do that, that's the lowest force possible. It means that you can print really thick parts, you get really high detail. The big thing I think is there's a ton of technology that is really sophisticated, but we've tried to keep it really simple. So this is preform, and this is how you get your prints ready to print on the Form 2. One of the new features is a feature we call one-click print. So I can actually go and open a few files, and with one click, it will lay them out, put them on supports, orient them. So again, just trying to make it really easy for people who want to use the printer.
When we built the Form 1, we were building really the simplest stereolithography machine you could build. We stripped it down to the most basic set of components, and part of that is we wanted to really make the thing as simple as possible, and part of that was what we could build at the time with the resources that we had. Since then, we've shipped thousands of them, learned a lot from our customers, and now we have the resources to build really the desktop stereolithography machine that we wanted.
So you went from the easiest to build with the most common parts to something that's a lot more complex, right?
Yeah, a lot more complex, but actually easier to use. We think that the Form 2 represents like a third generation of 3D printing, where in the beginning, since the 1980s when 3D printing was invented, people were building these industrial machines, really big, expensive things, hundreds of thousands of dollars, that were used when somebody needed something that only 3D printing could give you. And then around 2008 or so, people started to build these desktop machines, and we got really excited about that, and it was amazing to take the capabilities, some of the capabilities of these big machines and put them on the desktop. But most of the people using them were sort of either hobbyists or using it because they were excited about the technology and not yet getting a lot of value out of it. And so we think with the Form 2, we're entering sort of a third generation.
Okay, let's stop here. So one thing you might notice in this video is there is a step which is a blade move from one side to another side in order to separate the part from the bottom of the tank. If I draw some illustration, it's something like this. So let's say this is the tank, right? And the part actually is something like this. Basically, this is the build platform. And the part is it will be stick to the build platform in the upside down direction. And basically here, when the light cure the layer at the bottom of the tank, basically the layer will stick to the bottom tank as well. Although it may not be that strong bonding between the layer and the bottom of the tank, but still you want to cut it off using a blade to separate them. And although we already use some material like PDMS, which is the non-dig film, you can think of this as a Teflon, something like Teflon, right? So that means it's very hard to stick to such a material, but still there will be a weak bonding between the cured layer and the bottom of the tank. So you want to separate them, and then spread material, and then continue this curing again. That's how this kind of inverted stereolithography work. Any question for this? Okay, let's move on. So as I mentioned, these two, the 3D systems ones and also the Formlab ones are the two main process and in the market. So there are several differences. First of all is the laser sources. The 3D printer, the 3D system ones is a industrial grade laser. It could build a large part, but for the Formlab one, the cost is much lower. It's a Blu-ray laser diodes. And the laser orientation are different, right? For the 3D system one, it's projected from the top-down direction. And Formlab ones project from the bottom through a window. And the size of the laser, basically the 3D system ones can build much larger parts. The reason is if you build a larger parts using the Formlab process, basically that will make the separation of the newly built layer and the bottom of the tank difficult. So you cannot really separate easily. The separation force will become larger and larger, and turns out fail this process. So that's why the size, the part size is the limitation for such a process. And but it has advantages in terms of Ryzen usage. Why? Because just imagine if you have the same part to be built using 3D system or Formlab, basically for the 3D system machine, basically you need a full tank of material, which will at least as basically this depth is at least equivalent to the height of the part, or even larger, right? But for the Formlab process, what you want to do is you only need a small amount. You just need the Ryzen, which is right enough for building the parts, because the part only needs to have the material fill in between the gap. Fill in the gap in between of the previous layer and the bottom of tank, right? That's it. You don't need to have the whole part to be inside the Ryzen all the time, which is the case for the 3D printing, 3D system process. So that's the reason the usage of the Ryzen, basically the Formlab process has an advantage in terms of the amount. Any question for the difference? No? Okay, good. So regarding, because of all these difference, the 3D system ones usually have a larger, have a more expensive price, and the Formlab one is even more affordable. So another thing you might also need to keep in mind is the material, because of the process for this one. Basically, you need to scan through the Ryzen and also the bottom of the tank. So the Ryzen must to be transparent, right? If the transparency of the material is not good enough, basically the laser cannot be cannot be penetrate the material to cure it effectively. But for this one, it has less restriction because basically every time you are curing the resin, which is on the surface. So that's another difference between the two processes. And again, because the price for formlabs is much lower, that this we have such a printers in our lab sessions, right? It's more affordable. And let's talk about the build time for such a process. No matter the Formlab ones or the 3D system ones, still there is a laser scanning. So let's suppose the laser scans at this VS millimeter per second, and the cure traces are WT millimeter wide. So if you look at what the laser scans from the top view, that's how it looked like. And also, let's see, the layer thickness is LT millimeter. So if we want to build a part has overall volume to be like this, to be something like this, and also the overall part height is H. Then let's estimate what will be the overall time required. So let's think about what will be the main time factors in this process. Any idea? Just to think about the process. And here show you the path of the layer for of the laser scanning for each of the layer. So basically, it just scan along these passes is this kind of zigzag passes for one layer. Any idea? Okay, so in principle, that should be 2 times associated with the process. One is the time to scan each of the layer, right? And because of in both of the two process, there will be a time consumed in between of the 2 layers. So basically, you want to spread the material or separate the part from the bottom of the tank. But no matter how, there will be a time associated with with the process in between of the 2 layers. So you want to count both of the 2 times and sum them together to get all the overall time. That's how you think of this build time. So I can show you the result. To compute the laser scanning time. So what you want to do is to compute the volume scan rate. So how you come up with it? So you have the linear speed for the laser scan VS, and you have the trace width, right? That is WT, and also a laser thickness. Basically, put them together, you will have the volume scan rate. And since you have total volume like this, and the volume scan rate like this, so use the this total amount of volume to over this volume scan rate, and turns out that will be the total laser scan time. That's only the laser scanning time. Then let's talk about the time in between of the 2 laser scanning. Now we have the overall height to be H, and the layer thickness to be LT. And it turns out we have the number of layers. So for each of the layer, there will be a there will be a handling time. And let's assume the time needed to spread the resin in between of the layer is TS. Let's assume this will be the time required in between of the two layers. And use this TS multiplied by the overall number of layers, and that will be the overall time to for the handling in between of the two layers. I mean, it could be the spreading of the resin, or it could be the spreading of the resin plus the separation. So it depends on the process. But no matter how, there is a time required in between the two layers, right? And then you just add this and this together. That will be the overall time to build a part. So any question related to this? Okay, that could be some question associated with this one, right? Basically, given a volume of a total part and give you all these numbers, estimate how long it takes, right? Something like this. Oh, that's not available. But I think I can probably show you by click on the link. No? Huh. Anyway, I think there is some other other video available, but that is another process, which is the image projection-based stereolithography, and it was developed by InventionTech. Oh, by the way, InventionTech has been acquired by Desktop Metal just in this year. Basically, the idea is different from what we had for the 3D Systems and Formlabs machine, which is utilizing the laser scanning, right? InventionTech utilizes a projector, the digital light projector, to project a 2D image, black-white image, and this black-white image will cure the resin simultaneously. Basically, the white region will be cured and the black region will not be cured. So that's how it works. So the advantage here is it reduces the build time substantially because there's no laser scanning anymore. The cure happens when the image is projected and wait a little bit time. So an entire laser will be cured simultaneously at the same time for this process. And that's why the building time is reduced. Let me try to search. I think there are some other videos, but let's search the InventionTech process. I think there is someone. Yeah, let's look at it.
Question.
Yeah.
Why the companies or whatever prefer the laser like a Formlabs company over an imaging curing that is, for me, is more quickly processed and the definition or the accuracy is good too. So what is?
Yeah, that's a good question, and I will answer the question after I show you this video. All right. Yep.
Dental equipment needs to be very, very accurate. So when you're thinking about doing temporary crown, dentures, night guards, you gotta have a very, very accurate 3D printer. Denko is a dental CAD/CAM solution center. Our goal is to bridge the gap between leading digital dentistry manufacturers such as EnvisionTech with the small to mid-sized dental laboratories and dental clinics throughout the US. I think 3D printing technology works well with the dental CAD/CAM solution because in 3D printing, you don't have any limitation. Currently, we have a Vita for the variety material choice, and then we also had a Vector HD for the most accurate model printing with the full capacity.
For models, they are simply ditched and hollowed so that they can be printed accurately. The dentist either takes a traditional impression of the patient's current teeth or takes an intraoral scan of it. These impressions are either scanned or imported into the design software, where trained technicians take into account the doctor's prescriptions and dental anatomy to design the product. After this is done, the designs are transferred to our manufacturing department, where they are loaded onto the machines and printed. We use the eModel Light resin for our models.
I think EnvisionTEC model printing is the best in current market compared to any other 3D printer company out there. The reason being is the density of the solid model. It's much stronger and very, very smooth finish.
We have used a few other leading brand 3D printers in the past, but none of them have had the material delivery and applicability that EnvisionTEC had with their FDA-approved materials.
With the Vita, you can actually print anything you imagine, really.
We can print models, copings and metal framework partials, night guards, implant surgical guides, temporary crowns, wax crowns, and even dentures.
EnvisionTEC recently released the eDenture-based material. It's the first FDA approval denture-based 3D printing material. It can work with the eDent 400 to make a full digital denture prosthesis.
We recently developed a digital smile design solution that can transfer 2D smile design data into a 3D mockup that will fit into the patient's current existing teeth.
So once we try it in the patient's mouth, the patient emotionally feel the difference before we even start the procedure.
Digital dentistry is a rapidly evolving field, and as such, the ideal 3D printing company must have an outstanding R&D team that will never stop pursuing the next innovation.
As the president of Dencore, I believe EnvisionTEC printers produce the best quality for dental applications.
All right. Sorry. So yeah, I think the question is basically why we still need the lasers, right? There are two main reasons. One is compared to the laser, this kind of a 2D projection-based process cannot print relatively larger parts because of the image projection has a limit of the projection size. So just imagine you have a projector, right? If you project it in like 2 square feet, something like this region, the image will have a very clear look, right? But if you project it even larger and larger, then the image will become blurred, and that will essentially produce a inaccurate model if we use the projection to cure the resin. But for laser, because it depends on the laser, although for the laser you can still there's still limitation for the spot size. You cannot print any features which is smaller than the spot size of the laser, but we can make the laser spot size very, very small. So in that sense, if we compare the accuracy, the laser one will has a better accuracy compared to the projection based. But the efficiency for the projection based one is much higher. And that's why this is an emerging area. There are new startup companies producing more and more projection ones for the consumer level market. Like the one showing in the video, if we talk about some customized teeth, right? Or some teeth aligner, that shouldn't be an issue. It's not that big. So you can easily use the projection-based printer to produce it. Yeah, that's pretty much the reason for why there's still laser, and why we don't just use the projection based for all the applications. All right. I think we might stop here for a break. Let's go back 10:05. All right. Okay, let's continue. So there's another variations of stereolithography, that is without tank, there is a transfer film, and when printing each of the layer, the material is spread on a thin on the plastic film, and then the laser will be projected to cure that layer, and then again another new material layer will be spread onto it again and again. So for this process, the biggest difference is it does not require a resin vat. Let's look at how they work. So one layer is cured, and then the part is lifted, and the new liquid material is spread onto the plastic film. And then the part will be put back, another layer will be cured. Let's look at it. See? So it's similar to those projection-based, image projection-based process, right? The only thing is there's no tank or the resin vat required. So let's look at some emerging technology, which is called continuous liquid interface production, CLIP process. And this process is invented by a group from Duke, and also their group launched a startup company called Carbon. And let's look at what their process looks like.
Digital light synthesis combines Carbon's CLIP technology and programmable liquid resins to enable end-use parts with exceptional surface finish and unmatched mechanical properties. This screw compressor rotor is at the heart of the company Nativus's groundbreaking air conditioning unit. Advanced, highly efficient compressor designs like this one were previously found only in industrial compressors because the traditional CNC technology needed to fabricate them is expensive. With Carbon, Nativus was able to print the rotor in an advanced material called cyanate ester at a fraction of the cost of the CNC alternative. Here's how Carbon's technology works to print end-use parts. Light from a custom high-performance LED light engine projects a sequence of UV images exposing a cross-section of the part, causing the UV curable resin to partially cure in a precisely controlled way. Oxygen passes through the oxygen-permeable window, creating a thin liquid interface of uncured resin between the window and the printing part, known as the dead zone. The dead zone is only a third of a human hair thick. However, it is the area responsible for Carbon's remarkable high-performance resolution and unique isotropic parts. In the dead zone, oxygen prohibits light from curing the resin situated closest to the window, thereby allowing for the continuous flow of liquid beneath the part. Just above the dead zone, the UV light projected upwards causes a cascade-like partial curing of the part. Simply printing with Carbon's hardware alone does not allow for end-use properties with real-world application. Once the light has shaped the part, a second programmable curing process achieves the desired mechanical properties by baking the part in a thermal bath or oven. Programmed thermal curing sets the mechanical properties by triggering a secondary chemical reaction, causing the material to strengthen, achieving the desired final properties. Carbon is taking manufacturing from analog to digital, printing end-use parts with exceptional surface finish, unmatched mechanical properties, and real-world impact. Carbon, stop prototyping, start producing.
All right. So can you tell me what's the biggest difference between this new process from what the existing one? Any idea?
Maybe the oxygen produced like an oxidation or something, chemical process. I don't know.
Okay.
It could be that the resin here is actually flowing as opposed to the resin in the current process is still.
Yeah. I think
I'd
both.
imagine there's some sort of print time restriction as well, given that the layer height is, as they said, 1/3 of a human hair thick.
Yes, I think all of you have touched the points of the different. So basically, if you look at this this figure, the layer, I mean the resin and the tank, bottom of the tank, actually they are not they are not stick together. There is a oxygen window which prevent the curing happens, which is called dead zone in the video in this process. And the benefit is, do you still remember when we calculate the time for printing a part? So there are two major factors. One is basically the laser scanning time. In this case, it's the in this case it's the image projection and the curing time, right? That is related to the volume of the parts. And another portion of the time is the handling time in between of the two layers. No matter there is material spreading and also or there is even a separation of the layer also. But still, in between of the layer, there is a required time. So basically in this process, because the material, I mean the resin at the bottom actually does not stick to the bottom of the tank, that that handling time in between of the two layers actually are removed. So that greatly speed up the process. And that's why they, in their basically in their advertisement and in their paper, they claim they have like 100 times speed up compared to some other process. That's the, I would say, biggest advantages of this process. And because of this time reduction, one thing they could achieve is the continuous lifting the parts and the continuous cure the parts, such that the layer becomes much more compared to other stereolithography process. And that's why for the part they show in the video, it looks like a injection molded part. The density is so high. So that's how it works. As I mentioned, let me show you this video. As you can see here, the material resin flowing beneath the part continuously, And because of that zone, which has oxygen in it to prevent the curing, this region will prevent the sticking of the part with the bottom of the tank. So that's how it works. But there is a problem, fundamental problem. I mean, everything looks so good, but still there's no free lunch, right? They achieve this continuous lifting, continuous process. But if that's the case, why other company still there? Why this carbon didn't take over the whole market? The reason is, well, if you do something like this, this process is still limited to a small size part. Why? Because let's imagine if the part is large, that means this region is a big region. Even you can lift the part, even there's no bonding between the part and the bottom tank in the dead zone. But still, if this area become large, it takes too long time for the liquid to flow in. It's not water, it's some liquid resin, which has much more viscosity than water and the other liquid. So that means it's not easy for them to flow in a small region. So if the area is very large, very big, it will take much longer time for this. And that's the fundamental limitation for the process. So that's why in their videos, in their advertisement, they only show the parts with a small region of the contact, small cross sections, because for the large one, they still have problems. Any question? All right. So again, there's no free lunch for each of the process. Why they do this? Why they don't do that? There is a reason. It either from the fundamental physical or chemical principles, or from some consideration of the cost and efficiency. Basically, you need to think of these when you look at certain applications, when you look at these processes. But let's do a little comparison. Let's look at the key differences between the continuous liquid interfacing process and the Formlab process. So for the Formlab process, the adhesion force for the part sticking to the bottom of the tank, the sticking force to the inverted platform must exceed the separation force of the part separating from the bottom of the tank, right? That is must satisfied. Otherwise, when the separation happens, the part will be fall down to the tank, right? But in the clip, this seems to be solved because there is a dead zone over there to prevent the sticking of the part with the bottom of the tank. But still, it's limited to small size of part because of the reason I just mentioned. Well, if the cross-section area is large, it takes much longer time for the liquid resin to flow in the dead zone. To flow in the region, the dead zone region, to prepare the next curing, right? That's the different. Basically, for both the clip and also InventionTech's process, they utilize the projected image to cure the resin. And what other information you need to estimate the build time for this process? Basically, because of there's no such a handling in between of the two layers for this clip process. So the building time will be only related to how many layers. and how many for each of the layer, how long it takes to cure one layer, right? That's the only time left for this clip process. So you don't have the time in between of the two layers. So actually, this kind of stereolithography process can be utilized to make to make parts using other material like even ceramic or even metal. I saw some new work using metal powder based on the stereolithography process. And how? So what they do is they utilize the the resin material, those polymer material as the binder. So they basically mix the powder of ceramic or the metal with polymers, and then do the similar thing as the normal stereolithography does, and build the part. But that part is so-called green part, means it does not have the material, those metal particle or ceramic particle fused together, right? It has no stiffness. What you want to do is you want to do the debinding to burn out those polymers, and then do the sintering. That is to heat up the parts to a high temperature to actually fuse those particles, either the ceramic or the metal particle together, and then cool down naturally to have the final parts. So that's how people utilize the stereolithography to build ceramic or metal parts. Simple, right? But the thing is, you have the capability of 3D printing, which could produce a complex geometry. And that's the benefit to use the stereolithography process. Another interesting area people are looking at using the stereolithography is those organs, right? If you use the biodegradable material polymers, you could build really complex structures which human organ has. Another thing is you could customize the size and the geometry and even function of the organs if you use a 3D printing, specifically stereolithography. That's another very interesting area to look at. So there are multiple, I would say, popular area in using 3D printing. One is metal printing processes. Another one is this stereolithography, because it's related to many bio-related applications. Of course, the jetting is another one, which we will introduce in the following lectures. Any questions? All right, let's move on. So let's take a close look at those details. One is a key parts, key components in those laser scanning based process, which is the laser galvanometers. So basically, this galvanometer has two mirrors here and here. One is in first axis, we can take it as the x-axis. Another one is the y-axis. It has a rotation along two axes, here and here. This is x, this is y. If I create the coordinate like this, and each of the mirror will rotate along these axes, and together it could guide the laser to all different directions and cure the resin. That's how this laser galvanometer work. Because even you rotate a small angle in the x, with respect to x-axis and or y-axis, the laser could change its location when cure the resin quite a bit. So that makes the laser move very quickly. And if you look at this video, you could see some of the example, how this guide the laser to cure. Just 1 second, let me play the video.
The secret are galvanometers. Now, these are 2 mirrors, and each one of them is mounted to a galvanometer. A galvanometer is kind of like a very precise motor. There's a coil of wire and a magnet. When you put in a signal, it moves left or right. Can't
See
go
the
in a
2
complete
motors.
circle like a motor can. It's locked in position. These are general scanning
See?
galvanometers. You shine a laser so it hits one of the mirrors, bounces off that mirror, and hits a second mirror. One controls horizontal, the other controls vertical.
So with the two mirrors, the laser could move freely on this 2D plane. That is how the laser could scan on one layer, right? And here show you another similar setup for the galvanometer. See? So basically these components are borrowed from other process or other existing machines like the jetting printers also. So basically people utilize them in the new processes by modifying it accordingly, right? Another interesting component is this F-theta lens. Why we need this? If we look at those original spherical lenses, basically something like this. If you have some laser beam or light go through this spherical lens, it will be focused at certain point, right? Something like this. But on such a curved surface, basically their focus is on this curved surface instead of this plane. But what we want in the process is we want to have the focused laser spot on this 2D plane, which is where the one layer is located on. So in that case, you will always have those blurred spot instead of focused one, right? And that will essentially affect the accuracy of your printing. So that means a simple spherical lens will not do the job for the these laser scanning based printers, 3D printers. So instead, we have such a F-theta lens. So these F-theta lenses are a series of lenses which will essentially compensate this effect. Turns out it will make the focus of the laser still on a 2D plane. And that's where you want to put your layer is. And turns out you will have your laser has a focus on the 2D plane. So that's what the F-theta lens does. Any questions? All right, so you got it? Okay, let's move on. So for the projection-based process, a very important component is such digital light projection. And there is a mirror array like this. So it has a series of small mirrors, and each of the mirror can change their orientation a little bit, such that it could change the projected image with different intensity and also and different different geometry as well. So I think it's a video, right? No. Yeah, it's not a video, but that is the same mirror array utilized in the projector. There are processes using the visible light. Also, there are some projector utilize the ultraviolet or near infrared light. It depends on the material to be cured, but it has similar working principle as the normal printer. I still remember the first one, a digital light printer built in my lab when I was a PhD student, was utilizing a normal printer, which we use for our group meeting. Same thing. The only thing is the power is maybe a larger one, in order to have enough power to cure the material. But that's pretty much what it does. Each of the mirror could be tilted in different orientation to control the image. All right. So for the process, as you can see here, basically you are looking at an image to be projected, and the image pixel is fixed, right? Basically, you have an image with like different resolution. For example, this is a resolution, and this is another one, and that is depending on the macro mirrors array size. That means you have that much of macro mirrors, which is, for example, this one is 1920 by 1080. So, and that limits what are the maximum pixel you could provide for the image. Then, given these information, how could you calculate the theoretical maximum 3D printed feature size? So if we look at the image to be printed, you can basically there are two angles, projection angles, in both X and Y direction. For example, this one, it has 26 degrees in, for the X-axis and 18 degrees for the Y-axis. And with these two angles together with a image resolution, let's see this one, and also a distance between the image to the projection plane, which is where the horizon located. That put them together, you could have the maximum, I mean the minimum features this printer could produce. And let's look at how we come up with this. For example, we have an image. Where's my, yeah, here. Yeah, we have an image resolution 1920 by 1080, right? And also the distance of the lens to the projection plane is 40. And what is the smallest feature of the printer can print? So what you want to do is, well, you in the X-axis, right, to compute what will be this length, right? How could you know? Basically, you've already know this projection, the distance from the lens to the projection plane is 40. That means this one is 40 millimeter. And then compute this, because this is half of the dimension in the of the projected image in the x-axis, right? And how you compute? Use some trigonometry, right? This is 40, and this is half of 26, and which is 13, right? And then you could use the tangent function. Basically, tangent 13 times 40 is the length of this. Basically, when you have this times 2, then you have the full length here, which is something like this. And that is the projected image in the x direction. Same thing happens in the y direction. Again, this is 40, this is 9 degree, and this is tangent 9 times 40, and then times 2, you have the length in the y-axis. And now you have the projected image in x to be 18.5, and in y it's 12.4 millimeter. Still, for the image projected, it has a resolution 1920 by 1080. That means if we look at the projected image, it's still be composed by those small pixels, right? And you have the x dimensions length to be 18.5 and the y to be 12.7. Let's see, this is x, this is y. And you already know, okay, along the x-axis, there are 1820 pixels. And along y, it's the 1080. Then what is the unit length of the pixel of 1 pixel along x, and what is the length of the pixel along y-axis? Then use this 18.5 over 1920, and use this 12.7 over 1080. You will have the dimension of 1 pixel, and that will represent, that will indicate what is the minimum feature this printer could produce, right? Because that's the smallest unit this printer could produce. All right, any question? Any question for this calculation? Okay, basically this, you need to be very careful about this, and there could be questions. Again, sometimes you might, there could be different conditions given to you. For example, for some question could asking for what is the distance? If we have the image resolution and as well as the image size given, right? And also those angles. Some of the problem could asking for the angles if all other conditions are known. but same thing, just same logic. That's how you come up with these solutions. All right. So another details is about the wavelengths of those lasers, right? That could be different light utilized, like ultraviolet, violet, or blue ray. And you can see there are different wavelengths. And these different light sources are utilized for different resins, different materials. Basically, you need to decide what kind of light source to be utilized, which are compatible to other to the resin material you will be using. Right here shows you some informations for the light sources. Let's have little discussion about the stereolithography process. So first of all, what kind of material property leads to higher accuracy? I would say the shrinkage. As I mentioned, there will be a shrinkage after curing. So if it's just similar to the thermal shrinkage, if the shrinkage is smaller, that means you have much more control on the shape accuracy. So if the material has a smaller shrinkage, then the final part has a higher accuracy. Also, there are some applications require higher temperature resistance, especially for the ones like the there are some parts which will bear a high temperature. For those ones, you definitely want to have a higher temperature resistance. And there are some applications require the optical clarity. For example, there are some applications for 3D printing the lenses. So for the lenses, definitely you want to have a very clear material to be used. And there are some applications requiring lower stiffness. For such kind of applications, you're looking at some movable parts like the leading hinges. That means there are mechanisms, there are some coupled parts together, which has a motion, relative motion in between the parts. And in that case, you don't want to have the part to be brittle or too rigid. Instead, you want to have a flexibility, and that requires some low stiffness and more, I would say, the flexibility. I think it's a little still early, but I want to stop here since we just complete a whole topic for the basics of the process. And for the next lecture, let's talk about some of the computation, especially some of those laser energy computation. That's very important as well to have a full understanding about how the laser or the light source work during the process for the stereolithography. But for this class, let's just stop here. All right. Any questions?
Yeah, can you just remind me when, or say in general, when the office hour is? When's your office hour?
Yeah, that's Friday, 1 to 2.
1 to, okay, cool.
Yeah, 1 p.m. to p.m. I will be here this Friday to answer your questions regarding the exams and also homeworks, the 2 homeworks, and also projects.
And also, will you have homework 2 complete? I'm guessing homework 2 is going to be on the exam. So is that going to be like, are you going to grade that and give that back to us before Monday?
I'm not sure I can grade them all, but I will give you the solutions definitely by Wednesday.
Cool, thank you.
Any other questions?
I have a quick question.
Yeah.
Just regarding the homework, I think it was the problem about trigger points. How do you know which order to print when it comes to trigger points?
Oh, you mean the calculation, right?
Yes.
Okay, let me look at the trigger point, right? You're talking about trigger point. Let's look at the figure. It might be easier to look at on the figure. So basically, the trigger points are the intersections between the cutting plane, which is the one layers plane, right? And a triangle and a triangular edge. So actually, the order will be. It doesn't matter. It doesn't. Basically, the only thing matters is the order of trigger point for one layer, right? And how you order them, basically what you want to do is, let me show you here. So for example, you have the information of the triangle. Let's look at this triangle solely. For example, you found out the 2 trigger point on the triangle. That's definitely possible, right? And then you found another 2 trigger points in another triangle. So when you order them, what people usually do is starting from one triangle with the 2 trigger point, and the search is neighboring triangles. It has multiple neighboring triangles, right? In this case, this triangle has all these neighbors, but there are some data structure will record, well, in which triangle there are other trigger points. In this case, there's only one triangle, this one, neighboring triangle of this, has a trigger point. Then compare these 2 set of trigger points and find the overlapped one. Then now you have a bigger line segment like this, right? And then expanding from this bigger line segment by searching the neighbor of these 2 triangles, which are these ones, these ones, these ones, and this one, right? Again, find the one with trigger points in that triangle. There are some data structure to do that. Basically, that will indicate at which triangle there are trigger points or not, and what are they. That there are some data structure to do this. So let's see, in this case, you will find out these 2 trigger points again and compare with this larger line segment and find out the overlap. Then merge the line segment to an even larger one and repeat this again and again. You will have a complete line, and turns out it's a loop. It should be a loop. That's how people find out all the trigger points for one layer and order them together. It's a little tricky. It depends on the data structure of those triangles, but that's how people do it.
But
Did I answer your question?
Yes, thank you.
No problem.
I think that I misunderstood the question, I think, because I understand that the question was to indicate the order of the construction coordinates as an entire 3D printing part. That's not the question.
Well, so what's your question though? Can you say it again?
Because I understand that the question was to indicate the order of the construction coordinates in 3D for the entire part. So for example, the construction start with the point 1 that is 0, 0, 0. The next is 0, 0, 3, I guess. The other is the other.
Oh, okay.
And yes, that's the.
Well, that's a separate question. That means in some way you decide which direction will be the part building direction, and that direction will be set to be Z. For the simplicity of the computation, because you to compute all the trigger point, you've already assumed Z is the build direction, right? That's how you come up with the two equations. But that's separate from what I described previously, and that's a totally different question. How you decide the building direction, right? Usually decided by people, right? You will by checking the parts, you can tell, well, maybe build in this direction require less support or does not require any support. Or you want to have a like higher accuracy in certain direction, maybe lower one in other direction. Or in the composite printing cases, you want the fibers to be oriented in certain direction, then you choose that direction to be the build direction. All these factors, which are really hard to be considered by some algorithms, usually still decided by humans, right? All right.
Okay.
Any other questions?
I'm sorry. Now I'm confused. So for the question on the homework, for the first numerical problem, which part are you asking? Are you asking us to order the trigger points, or are you asking us to rank the order we would print the part like the last question was?
Just 1 second. Let me open the homework.
I think that's my question too.
Oh, okay.
Maybe you expressed better my question.
Yeah, I didn't notice. I didn't realize it. Okay. All right. You mean the
it's the third sentence of the first problem, of the first numerical problem. It says list the coordinates. It says list the coordinates in the order you would print them if you were fabricating this pyramid via a 3DP process such as filament extrusion.
Yeah. Oh, that's a good question. So basically, because in the for the contour, right? You will have counterclockwise order. Then here is asking you to list the points in the counterclockwise because there's no holes. If you check the slides for the exterior surface, the order of those trigger points should be in counterclockwise. If you're talking the loop on the interior surfaces is clockwise direction, but in this case, it's just a solid pyramid. That means there's no interior surface. It's all exterior surfaces. Means you want to list the points in the counterclockwise. Then what is a counterclockwise in this case? That's the question. If you print it still in the Z axis. Now you got it, right?
Yes.
Okay.
It depends. After we depend on that for calculate the area.
Yeah. Exactly. Exactly.
Yeah, it's okay.
All right. Any other question? Okay, good. If there's no more question, let's meet on Fridays, the office hour if you want to join. And otherwise, let's meet on Monday. All right. See you guys. Yep.
Thanks, Professor.
Yep.